Let's look at section 5.8, polynomials and several variables. Let's start with definitions. Polynomials and several variables describes a polynomial containing two or more variables. The degree of a polynomial is the largest degree of any of its terms. Let's look at this example where we have 2x cubed y minus 7x squared y cubed plus x y squared as a polynomial. The first term, 2x squared y, has coefficient 2, degree 3 plus 1 equal 4. So whenever a variable doesn't have an exponent, that exponent is an unwritten 1. To get the degree, we add the exponents. The second term is minus 7x squared y cubed, coefficient is negative 7. Degree is the sum of the exponents on the variable. 2 plus 3 equal 5. When we go to our third term, xy squared, we realize x has an unwritten power of 1 and the term has an unwritten coefficient of 1. So the coefficient is 1. The degree of the term is the sum of the exponents on the variable, 1 plus 2, which equals 3. The highest degree is 5, so that's the degree of the polynomial. Let's do the same thing for the polynomial 7x to the fourth minus 6. So 7x to the fourth is the first term. The coefficient is 7. The degree is 4. If the term has only one variable, the degree of the term is the power on the variable. The second term is negative 6x cubed y squared. The coefficient is negative 6. Notice how a term owns the sign in front of it. So when we're listing the terms, we don't have to write positives if the term is positive. But if a term is negative, we do have to write the negative. The coefficient of the second term is negative 6. The degree is the sum of the exponents on the variable, 3 plus 2, which is 5. The third term is 5xy. Remember that there's an unwritten power of 1 on both the x and the y. The coefficient of this term is 5. And the degree of the term is the sum of the exponents on the variable. So the exponents on the variable are unwritten 1, so the degree here is 2. The degree of the polynomial is 5, since that's the degree of the term with the highest degree. The leading term of the polynomial is negative 6x cubed y squared, the term with the highest degree. The leading coefficient of the polynomial is the coefficient of the leading term, which is negative 6. So let's complete the table for the polynomial listed here. And this has 4 terms, so we're going to have to add an extra row to our table. So the first term of the polynomial is 6x to the 5th, coefficient 6, degree 5. The exponent on the variable is 5 since there's only one variable. Negative 4x cubed y squared is the second term. Its coefficient is negative 4. The degree of that term is 3 plus 2, which is 5. The third term for the polynomial is 5xy. Remember, there's an unwritten coefficient of 1 on both the x and the y. Coefficient is 5. Degree is 1 plus 1 equal 2, the sum of the exponents on the variable. Negative 8xy to the fourth is my fourth term. There's an unwritten power of 1 on x. Coefficient negative 1, degree 1 plus 4, which is 5. So the degree of the polynomial is 5. The leading term of the polynomial, there is no leading term. So instead of writing none, I'm going to write DNE, and that stands for does not exist. So the leading term doesn't exist because more than one term has the highest degree. There is not a single term with the highest degree. In other words, there is not a single term with the highest degree. Therefore, there is no leading term, nor is there a leading coefficient. So to have a leading coefficient, you have to have a leading term. And notice there wasn't just one term that had the highest degree, but there were 3 terms that had the highest degree. Term 1 had the highest degree of 5. Term 2 had the highest degree of 5. Term 4 had the highest degree of 5. So in order for there to be a leading term, there has to be exactly one term with the highest degree. So sometimes when a polynomial has more than one variable, there is no leading term. If a polynomial has a single variable, there will always be a leading term. We evaluate polynomials and several variables the same way we evaluated algebraic expressions in section 1.5. We substitute the given values for the variables and evaluate. Evaluate means find the value of. So here, our polynomial, we are going to replace x with -2, a green -2, and y with a red 3. So we're going to color code it. And the first thing I do is replace every variable with its given value. Good form is to put these variables in parentheses. Then I apply the order of operations. First, I evaluate exponents. Then I multiply. And then finally, I add. And the result is 149. So let's evaluate this polynomial for x equal -1 and y equal -2. Let's start by replacing every variable with a parenthesis. This is the ideal first step for this problem. Now let's color code it, and let's put a green -1 in each parenthesis that replaced x, and a red -2 in each parenthesis that replaced y. And of course, you don't have to use colors when you work this problem on an exam, but what you should use are the parentheses. Because when I raise a negative value to a power, I need to parenthesize that negative value to write it correctly. -1 to the even power of 4 is +1. -1 to the odd power of 3 is -1. -2 to the even power of 2 is 4. And notice whenever I raise a negative to an even power, the result is positive. When I raise a negative to an odd power, the result is negative. Now let's carry out our product. 7 times 1 is 7. -6 times -1 times 4 is +24. 5 times -1 times -2 is +10. And when we add that, we get our final result of 41. So when we multiply polynomials in several variables, we're going to do it just like we did when the polynomials had a single variable. We're going to use the distributive property, and we're going to use the special product rules from section 5.5. Let's look at this example where we're multiplying 5xy squared by a trinomial. Every term of the trinomial gets multiplied by 5xy squared. And then I use the rules of exponents and the rules for multiplying monomials. My result is then found. Let's find the products for number 7a. We want to multiply this binomial by the trinomial. So we are going to take every term of the binomial, so 3xy, needs to get multiplied by every term of the trinomial. We'll write the 3xy in red. The other term of the binomial, positive 2x, also needs to get multiplied by every term of the trinomial. Notice what we're doing is we are using the distributive property twice. Also notice that two terms in one polynomial times another polynomial that has three terms is going to result in 6 products. So 3 products come from me multiplying 3xy by every term of the trinomial. And then 3 products come from me multiplying 2x by every term of the trinomial. So when I multiply 2 polynomials, the number of products is the product of the number of terms in each polynomial. So 3xy gets multiplied by 7x to the 4th. 3xy gets multiplied by negative 6x cubed y squared. 3xy gets multiplied by positive 5xy. Positive 2x gets multiplied by positive 7x to the 4th. Positive 2x gets multiplied by negative 6x cubed y squared. 2x gets multiplied by positive 5xy. So 3 times 7 is 21. X times x to the 4th is x to the 5th. I copy the y. Negative 3 times negative 6 is negative 18. X times x cubed is x to the 4th. Y times y squared is y to the 3rd. 3 times 5 is positive 15. X times x is x squared. Y times y is y squared. Positive 2 times 7 is positive 14. X times x to the 4th is x to the 5th. Minus 2 times positive 6 is minus 12. X times x cubed is x to the 4th. I copy the y squared. 2 times 5 is positive 10. X times x is x squared, and I copy the y. There are no like terms here, so there is no simplifying for me to do. This is my final answer. Here in 7b, I'm multiplying 3 binomials. I'm going to work with them 2 at a time. So I'm going to just recopy x plus y, and I'm going to multiply x minus y times x plus y. And hopefully you'll notice that this is one of my special products. X minus y times x plus y is a product of conjugates. This product results in x squared minus y squared. We talked about this special product in section 5.5. Now I need to multiply x plus y times x squared minus y squared. So x gets multiplied by every term in x squared minus y squared, and so does positive y. And I use the distributive property twice. X times x squared is x cubed. X times negative y squared is negative xy squared. Positive y times x squared is positive x squared y. Positive y times negative y squared is negative y cubed. There are no like terms to combine, so this is my final answer.